And welcome there, calculus folks. We've got a couple of examples to support the CEMC videos. Um, Harder examples, I'd say. This one is a proof that shows up at the end of 7.3. I'd say that most of the questions that you'll see today are thinking type questions. And this is a dandy one. Prove that the diagonals of a rectangle ABCD are perpendicular if and only if ABCD is a square. Well, that's special language in mathematics, if and only if. And what it means here, I'm going to show you. If and only if B means two, there's actually two things. If A is true, then B is true, which is a common statement in mathematics. But it's also, if B is true, then A is also true. So it's two parts to a proof. So what are we talking about here? We've got kind of our A is that the diagonals of the rectangle ABC are perpendicular, and the B part is ABCD is a square. So we've got two proofs, and here we go. So the first proof is we're going to say A, if A, then B. So what's the first thing we can say? Well, we are given A is true. So we are given that, and I'm going to use the grass technique for proving this, we're given that the diagonals of rectangle ABCD are perpendicular. So the diagonals are perpendicular. So if I have a rectangle ABCD that we know they're perpendicular, this is 90 degrees. That's what we're given. What we're required to show, and we're required to show that ABCD is a square. Notice that if I wanted to translate that, if I showed that AB is, because we know it's a rectangle, right? So we know AB is equal to DC, both in magnitudes and the direction as well, because opposite sides of a rectangle are parallel. We're given that. So all we would need to do then is show that the AB, magnitude of AB is equal to the magnitude of BC. That would be sufficient. Okay? Um, in my analysis stage, remember G for given, R for required, A is analysis, or kind of this is the brainstorming thing. What am I going to use? Well, diagonals are perpendicular doesn't really help me anything as far as math is concerned. Let's change that to a math statement. Well, that the diagonals are perpendicular tells me that the dot product is 0, right? That is that. And so this is going to be our given fact that we use. Some other facts that I'm going to use is I'm going to use some stuff that's true. Like, for instance, AC. I'm going to do this in a different color just to show you that this is kind of part of my analysis phase here. AC is, well, it's AB plus BC. Similarly, um, BD, that vector there is BC plus CD. Starting with something that's true, BC plus CD, and I don't need those brackets in there. That's not necessary. But what I am going to do, because at some point I can see if I'm going to use this fact and these facts from the diagram, that I'm going to use some properties of dot product. And in the notes, here's some properties of the dot product, right? There's the definition of the dot product, but there were some consequences that showed up because these are just scalars, that the order that I take the dot product doesn't matter, right? These are all scalars. These are all real numbers. It doesn't matter the order. So P dot Q is the same as Q dot P. The one that's going to come in really handy here is this idea of I can distribute the dot product over vector addition, right? So when I take P dot a sum, that's the same thing as P dot the first one plus p dot, the second one. It's distributive, just in the same way that we would think of algebra terms as being distributive. We can distribute the dot product. This one will come in handy later. This idea of a vector dot itself, while the cos of 0 is 1, the angle between a vector and itself is 0, so a cos of that is 1. And this one we won't use this time, but we might use later, is this idea of if I have a scalar times a vector, it doesn't really matter where I put it. I can put it in the first vector, I can write it out front, I can write it with the second vector, it doesn't matter. But this is the one that we're going to use quite a bit. Back to my proof. Now I'm going to put that in there. I'm going to go back to green. At some point here, we're into our, this is our solution now, I think. I've got AB plus BC dot BC plus CD. And you see what I'm going to do is I'm going to distribute this. I'm going to distribute the first vector addition and the dot product. And basically, it's just like good old grade 10 bracket times a bracket. It's FOIL, right? We've got AB dot BC plus AB dot CD plus BC dot BC plus BC dot CD. And that's equal to 0 because we knew the diagonals were perpendicular. Well, what do we have? AB dot BC. AB dot BC. Well, this is a rectangle, right? AB, if I think about this over here, AB dot BC, that's 0 because we have a rectangle. This is a 90-degree angle, so this is 0. Similarly, BC dot CD, this one's 0. And so what have I got left here? Well, I see that I've got right there BC dot BC. BC dot BC is just BC squared. That's gone. This is equal to, and what do we have here? We have AB dot CD. AB dot CD. Well, notice that CD is just negative AB. Following? Well, then what do I have? Well, there is that one rule. When I have a scalar in with this, I can write it out front if I wanted to. And now what do I have? Well, this is negative AB dot AB, which is the negative of AB squared plus BC squared, magnitude of BC squared. And what do I have now? I'm going to put that on the other side and square root both sides. And look what I have. Square root both sides. Therefore, ABCD is a square. Notice that that was just the first section. That was just if A, then B. Now I have to say if ABCD is a square, then it works the other way as well. And I'm going to do that. I'll do that on the next page here. So my given here is ABCD is a square. And I'm required to show that the diagonals are perpendicular, i.e., I need to show that their dot product is 0. It's almost the same argument with the details are a little bit backwards, right? So my analysis solution here, I'm going to sort of consider this. I don't know that it's equal to 0, but if I can show somehow that it is, then I'm going to be very pleased with myself. So what's AC? Well, I'm going to pull the same trick. AC is just AB plus BC, and BD is AB plus sorry about that. That's not AB. This is, let me get rid of that and draw a little picture here so I'm not goofed up. A, B, C, D. And here's my square. BD, that vector there is BA plus AD. And then I'm going to distribute again. Same trick. And what's going to happen? Do you see how stuff is going to cancel out and be 0? Yeah, it's going to. There. AB dot AD. Remember, we are given that this is a square. And then BC dot BA plus BC dot AD. What do we got? Vector dot itself in the opposite direction. I'm going to do a shortcut and just call that squared. AB dot AD. AB dot AD. Well, that's a square, so this is 0. BC dot BA. BC dot BA, though that's a square, so that's 0. BC dot AD. BC dot AD. Well, those vectors are the same. BC dot AD. BC dot AD is BC squared. But notice that since it's a square, I know the magnitude of AB is equal to the magnitude of BC. So therefore, this is 0. Therefore, there's my statement. The diagonals are perp. And this one, pretty big proof, an if and only if proof. I don't think you're asked for any of those in the homework, but at least it shows the properties of dot products used in a proof, and therefore, and I'm not going to rewrite it all. A if and only if, that's a short form for if and only if, by the way. B. All right, I'm going to come back with example 2, which is an algebraic example from 7.4 in part 2.